unveiling the Higgs particle, a landmark in modern physics. The identification of the Higgs particle stands as one of the most extraordinary feats in contemporary physics, not merely because it addressed a persistent scientific mystery, but also because it symbolizes the success of human creativity, complex engineering, and predictive theoretical work. The saga of the Higgs boson is a chronicle of endurance stretching across nearly 50 years, from its theoretical prediction to its eventual experimental validation. At its core lies a deceptively simple, yet profoundly significant question: what gives particles their mass? During the early 1960s, physicists were formulating what we now call the Standard Model of particle physics, a conceptual framework that would ultimately become the cornerstone for understanding elementary particles and the fundamental forces of nature. Although this model explained many phenomena, it had a critical shortcoming. It couldn't account for the masses of particles without violating essential symmetries that govern how particles and forces behave and interact. According to the mathematical equations of the time, particles such as the W and Z bosons, which mediate the weak nuclear force, should have no mass at all. Yet, experimental evidence contradicted this. These particles were, in fact, massive. Without a mechanism to explain mass, the Standard Model remained incomplete. In 1964, a group of theorists, including Peter Higgs, Robert Brute, Francois Englert, Gerald Guralnick, Carl Hagen, and Tom Kibble, proposed a bold new concept: the existence of a new field, which would later be called the Higgs field. Higgs proposed that this invisible field extends throughout the entire universe. As particles move through it, they interact with the field. This interaction effectively slows them down and endows them with mass. Certain particles, such as photons, pass through the field unaffected and remain massless, while others, like the W and Z bosons, strongly interact with the field and thus gain mass. To visualize this idea, imagine walking through a densely packed room. A person moving across the crowd is slowed by the interactions with the people around them. This is analogous to how particles gain mass while moving through the Higgs field. Depending on their intrinsic properties, some particles are affected more than others, leading to differences in mass. If such a field truly existed, it would logically result in the existence of a unique particle, the Higgs boson, which would be a quantized excitation of the field, essentially a ripple in the Higgs field itself. Proving this particle's existence became one of the most significant challenges in particle physics. But due to its expected high mass and the energy levels needed to detect it, the Higgs boson remained undetectable for decades. This challenge led to the creation of one of the most ambitious scientific projects ever undertaken, the Large Hadron Collider, LHC. Built near Geneva, Switzerland, the LHC is a colossal underground particle accelerator operated by CERN, the European Organization for Nuclear Research. Its purpose: to accelerate protons to nearly the speed of light and smash them together, replicating conditions similar to those just after the Big Bang. In these high-energy collisions, protons break apart and new particles are briefly created, potentially including the Higgs boson, if it exists. After years of design, construction, and calibration, the LHC officially commenced in 2008. Thousands of scientists and engineers from across the globe joined forces on experiments tailored specifically to search for the Higgs boson, especially the ATLAS and CMS collaborations. Detecting the Higgs boson was far from straightforward. Researchers had to identify incredibly faint signals hidden within a vast ocean of particle interactions. The Higgs boson decays almost instantly into other particles, so scientists had to detect its presence indirectly by analyzing the decay products and separating them from background noise. This demanded meticulous filtering and repeated analysis of the data. Finally, on July 4th, 2012, CERN scientists announced the detection of a particle consistent with the Higgs boson. Both the ATLAS and CMS experiments independently confirm this with high statistical certainty. The revelation was hailed as a historic scientific triumph. It completed the Standard Model by verifying the existence of the Higgs field, a fundamental ingredient that gives mass to elementary particles. The discovery made headlines around the world. Peter Higgs, present at CERN that day, was visibly emotional, witnessing the realization of a concept he had proposed nearly 5 decades earlier. Though nicknamed the God particle for its pivotal role in physics, the Higgs boson is more than a theoretical achievement. The Higgs field is critical to the formation of the universe's structure. Without it, particles would lack mass, making the existence of atoms, and by extension, stars, planets, and life, impossible. Beyond affirming the Standard Model, this discovery also opened new frontiers in physics. The Higgs boson may hold keys to understanding deeper mysteries such as dark matter, gravity, and perhaps new physics beyond the Standard Model. To further illustrate the Higgs field, picture the universe as a massive canvas. Particles are like paintbrushes. The canvas has a subtle resistance that affects how the brushstrokes behave. A thicker brush might drag more than a fine one, just as some particles interact more with the Higgs field, gaining more mass. The discovery of the Higgs boson is not just a conclusive moment, it's a gateway. Its unique properties may reveal clues about supersymmetry, extra dimensions, and unknown forces. Modern physicists continue to examine it with greater precision, hunting for anomalies or unexpected behavior that might signal new laws of nature. In short, the Higgs boson offers a deeper glimpse into the fundamental structure of our universe. It clarifies how particles gain mass, how matter forms, and what underlies everything we observe. The path to its discovery is a shining example of scientific perseverance, global collaboration, and unrelenting curiosity. And like all great breakthroughs in science, it answers one question, while raising many more. Detecting the echoes of the cosmos, gravitational wave breakthrough. Gravitational waves, undulations in the structure of space-time itself, stand among the most awe-inspiring and significant consequences predicted by Einstein's general theory of relativity. For more than 100 years, scientists hypothesized their existence, though they evaded detection and seemed unreachable. However, in 2015, following decades of relentless scientific pursuit, these intangible ripples were observed for the first time, confirming one of the most compelling forecasts in theoretical physics. This milestone opened a completely new chapter in astrophysics, allowing humanity to hear the universe in an entirely novel way. The idea of gravitational waves originated from Albert Einstein's revolutionary work on general relativity, published in 1915. This theory dramatically transformed our grasp of gravity, not as a force transmitted between masses, but as the bending or deformation of the space-time continuum caused by the existence of mass and energy. To visualize this, imagine space-time as a vast, stretched-out sheet or trampoline. When a heavy object is placed on its surface, the sheet curves inward. Smaller objects like marbles roll along the resulting dips and curves, following the distorted shape created by the heavier mass. Similarly, planets and stars travel along curved trajectories in the warped fabric of space-time. Einstein's equations also implied that moving masses, especially those undergoing acceleration, would create ripples in space-time. These ripples are what we call gravitational waves. Such waves are generated in dramatic cosmic events involving extremely dense, massive objects like neutron stars or black holes, especially during mergers, where they spiral inward and collide. However, even Einstein was uncertain whether these waves could ever be observed. By the time they reached Earth, their strength would be unimaginably tiny, making their detection an extraordinary challenge. The concept of measuring such subtle tremors in space-time was captivating, but the practical question loomed large. How could disturbances so minuscule ever be captured? Gravitational waves would slightly stretch and shrink space itself, but their effects on physical objects would be infinitesimal, far too subtle for conventional instruments to notice. Even the violent collision of two black holes would change distances by less than a fraction of a proton's diameter. This is where LIGO, the Laser Interferometer Gravitational Wave Observatory, entered the picture. The brainchild of years of theoretical and engineering work by scientists such as Rainer Weiss, Kip Thorne, and Barry Barish, LIGO began its construction phase in the 1990s with the aim of detecting these nearly imperceptible warps in space-time. LIGO's approach relied on a device called an interferometer, which tracks tiny changes in distance between two mirrors set miles apart. A laser beam is divided into two parts, each traveling along perpendicular arms. The beams reflect off the mirrors, then reunite. If a gravitational wave passes through Earth, it will distort one of the arms ever so slightly, causing a detectable shift in the light pattern as the beams recombine. Despite how tiny the alteration is, LIGO's ultra-sensitive technology can detect it. Then on September 14, 2015, at 9:50:45 UTC, LIGO accomplished what had previously been thought impossible. Both of its detectors, one in Hanford, Washington, and the other in Livingston, Louisiana, recorded a signal that could only be explained by a gravitational wave. The origin of the wave? The spectacular merger of two black holes, each approximately 30 times more massive than the Sun, located an estimated 1.3 billion light-years from Earth. The signal lasted under a second, but its distinct chirp revealed an escalating pitch and intensity as the black holes spiraled closer and finally united. This collision unleashed an amount of energy, within a fraction of a second, greater than the combined output of every star in the observable universe. That energy was carried across the cosmos in the form of gravitational waves, ultimately reaching and being detected by LIGO. This groundbreaking observation marked a pivotal moment in physics and astronomy. The verification of gravitational waves not only confirmed a century-old prediction from Einstein's theory, but also ushered in a new mode of cosmic observation. It was made possible by the collaborative effort of scientists across the globe, representing a powerful validation of decades of research, innovation, and confidence in a theory many had once considered unverifiable. The implications of detecting gravitational waves are profound. They provide a means to observe violent and energetic phenomena happening billions of light-years away, events previously invisible to telescopes relying on light or electromagnetic radiation. Gravitational waves carry information from some of the most extreme and mysterious environments in the universe, locations where space-time itself is warped and gravitational forces are overwhelming, such as in the case of colliding black holes, neutron star fusions, or supernova explosions. Before this revelation, astronomers could only explore the universe using electromagnetic signals, visible light, radio frequencies, X-rays, and so forth. But gravitational waves offer a completely different medium, enabling the study of phenomena that remain hidden to traditional observation methods. These ripples offer insight into the nature of black holes, the formation of galaxies, and the structure of space-time itself. For example, since the first detection in 2015, LIGO has identified multiple gravitational wave signals, including neutron star collisions, which are crucial for understanding cosmic occurrences like gamma-ray bursts and the creation of heavy elements such as gold and platinum. Gravitational wave science has now become a thriving field, expanding further as additional observatories come online. In Europe, the Virgo detector contributes to the global effort, and future missions such as LISA, the Laser Interferometer Space Antenna, aim to detect gravitational waves in space itself. The revelation of gravitational waves not only verified Einstein's insights, but also challenged our broader understanding of the cosmos. It has sparked new theories, raised fresh questions,
and introduced unprecedented methods for exploration. One particularly exciting frontier is the possibility of investigating the interiors of black holes, regions from which light cannot escape. Gravitational waves may enable us to glimpse into the core of these mysterious cosmic objects, offering an entirely new investigative lens. Moreover, gravitational wave detection presents a critical avenue for testing general relativity in extreme environments. Although Einstein's theory has withstood all tests so far, the ability to examine its predictions in domains where ordinary physics fails offers valuable opportunities for discovery. To help visualize the concept, think of standing beside a still pond and watching as a rock is thrown in. The ripples that spread across the water carry information about that event. Similarly, gravitational waves traverse space-time, transporting data about colossal cosmic incidents, like black hole or neutron star mergers, that generated them. Before 2015, these waves remained speculative. Now, they are among our most advanced tools for investigating the cosmos. Their detection marked the dawn of a new era in astronomical exploration, one that allows us to listen to the cosmos in ways once thought impossible, revealing a universe far richer and more enigmatic than previously imagined.
Unveiling distant worlds, the search for exoplanets, and the quest for extraterrestrial life. For ages, humans have gazed at the night sky, questioning whether life might exist beyond our home planet. The notion of alien worlds, potentially similar to Earth and brimming with life, has sparked the imaginations of writers and philosophers alike. Yet for most of our history, this remained purely a matter of speculation until science began to provide concrete answers. The confirmation of planets orbiting stars outside our solar system, known as exoplanets, has not only established that other worlds are real, but also opened doors to the possibility that life could exist elsewhere in the cosmos. But how were these distant worlds discovered, and what might they mean for the search for life beyond Earth? The journey toward uncovering exoplanets began not long ago, with the first confirmed detection occurring in 1992. However, that groundbreaking moment was the result of years of development, scientific theories, technological advancements, and a persistent curiosity. Back in the 1980s, astronomers started devising techniques to detect planets circling stars. But spotting exoplanets is far from simple. Stars are incredibly bright and distant, and their planets are usually hidden in their glare. It was astronomers Alexander Wolszczan and Dale Frail who made the revolutionary breakthrough. They didn't find a planet orbiting a typical star, but rather around a pulsar, a rapidly spinning neutron star with intense magnetic fields. The pulsar, named PSRB 1257 plus 12, emitted consistent pulses of radio waves. By observing slight changes in the timing of these pulses, Wolszczan and Frail inferred the presence of planets causing gravitational disturbances. Though the planets they found were harsh, rocky, and inhospitable, this discovery marked the first definitive evidence that planets existed beyond our solar system. Yet it was the 2009 launch of NASA's Kepler Space Telescope that truly transformed the field. Designed explicitly to locate Earth-like planets situated in the habitable zone, the orbital sweet spot around a star where liquid water might exist, Kepler revolutionized our approach. Its primary method, the transit technique, was both straightforward and ingenious. When a planet crosses in front of its host star from Earth's point of view, it causes a slight dip in the star's brightness. By meticulously monitoring thousands of stars for these subtle dimming events, Kepler provided data about the size, orbit, and potential makeup of exoplanets. Kepler's perseverance paid off. By 2012, it had identified over 2,300 candidate exoplanets, many Earth-sized, some even located in habitable zones. This milestone marked a turning point. Scientists were no longer just detecting exoplanets. they were beginning to discover potentially life-supporting ones. The detection of Kepler-22b, located about 600 light-years away and residing in its star's habitable zone, was especially thrilling. Though far from us, it demonstrated that such planets might be more common than we once believed. With technological strides continuing, astronomers rapidly expanded the catalog of confirmed exoplanets. By 2015, the number had surpassed 1,000, revealing a surprising diversity of planetary systems. Some exoplanets are super-Jupiters, much larger than Jupiter and orbiting incredibly close to their stars, while others, called super-Earths, fall between Earth and Neptune in mass. These discoveries overturned long-held theories about where and how planets could form. Besides the transit method, scientists developed other powerful techniques to uncover these hidden worlds. One is the radial velocity method, also known as the Doppler technique, which detects the gravitational pull a planet exerts on its star. As the star wobbles slightly in response, its light spectrum shifts, either redward or blueward depending on motion, revealing the presence of an unseen planet. Another technique is direct imaging, which involves masking the blinding light of a star to directly photograph its surrounding planets. While extremely challenging, it has led to striking observations, particularly of young exoplanets glowing in infrared light. These discoveries lead to a fundamental question. Are we alone? Given the sheer number of exoplanets, many sharing conditions with Earth, the possibility of life beyond our planet is more plausible than ever. In 2015, astronomers announced the discovery of Proxima b, located within the habitable zone of Proxima Centauri, the nearest star to the Sun. Though we can't yet confirm the presence of life there, the existence of such an Earth-like world so nearby gave rise to renewed excitement and urgency in the search for life. What's more, advances in spectroscopy have allowed scientists to begin analyzing exoplanet atmospheres. By studying light that filters through or reflects off an exoplanet's atmosphere, researchers can identify key molecules, such as oxygen, methane, or water vapor, that might indicate biological processes. This technique, known as atmospheric characterization, offers an unprecedented window into the nature of alien worlds and could eventually help identify planets with life-sustaining conditions. The pursuit of a true Earth 2.0 has become one of the most thrilling scientific endeavors of our era. While we haven't yet discovered a perfect twin, the thousands of known exoplanets, some with environments conducive to life, continue to provide hope. Upcoming missions and telescopes like the James Webb Space Telescope, JWST, and the Nancy Grace Roman Space Telescope promise even deeper insights, including the ability to scrutinize exoplanet atmospheres with exceptional precision. What do these revelations mean for us? The exploration of exoplanets is reshaping our understanding of the cosmos. It implies that we are not isolated beings, adrift in a lifeless universe, but rather part of a cosmic web filled with untold worlds and potential. Whether or not we ultimately discover extraterrestrial life, the very act of searching deepens our understanding of Earth, its unique properties, and our role within the greater expanse. By peering into these distant systems, we confront fundamental questions. What defines a habitable world? How does life emerge and persist? What is our place in this universe? The study of exoplanets serves as a compelling reminder that humanity is part of an extraordinary cosmic unfolding, one that is just beginning to reveal its wonders. Revolutionizing computation, the rise of quantum technologies and information science. In the 1980s, renowned physicist Richard Feynman famously remarked that, "If you're not baffled by quantum mechanics, then you haven't understood it." His words captured the bewildering nature of the quantum realm, where particles can occupy multiple states simultaneously, and information follows principles that seem to contradict traditional physics. Despite its strangeness, This quantum domain contains the foundation of a transformative leap in computing and information theory that may reshape our world: quantum computing. At its core, quantum computing is a radical method of information processing that leverages the peculiar behaviors found in quantum mechanics. The concept began to form when scientists realized that classical computers, which operate on binary digits or bits, might fall short when solving certain extraordinarily complex problems. Classical bits exist strictly as either 0 or 1. While this binary approach handles many computations effectively, it struggles with problems that demand extreme computational resources, such as simulating molecules at the quantum scale or breaking cryptographic codes based on large number factoring. In 1981, Feynman introduced a novel proposition. Rather than using conventional bits to simulate quantum systems, why not build a machine that directly utilizes quantum mechanics? Quantum mechanics, the branch of physics concerned with the behavior of matter and energy at atomic and subatomic levels, includes phenomena such as superposition, being in multiple states at once, and entanglement, a deep connection between particles regardless of distance. Feynman envisioned a device that could capitalize on these properties to model quantum systems far more efficiently than classical machines. This idea was a key moment in the birth of quantum computing. Feynman wasn't alone in exploring these ideas. In 1985, Oxford physicist David Deutsch advanced the field further by formulating a theoretical framework for a quantum computer, now known as the Deutsch model. His work laid essential theoretical foundations for how quantum computers could operate in practice. To grasp the functioning of quantum computers, we must first understand two central quantum phenomena: superposition and entanglement. Superposition means that quantum particles, like electrons, don't reside in just one state at a time. They can exist in several states simultaneously. Picture flipping a coin. It lands either heads or tails. In the quantum world, however, the coin remains in a blend of heads and tails until observed. Quantum computers exploit this effect by allowing qubits, the quantum analog of bits, to be in both 0 and 1 states at the same time. This capability vastly increases their processing power, enabling them to handle numerous calculations in parallel. Entanglement occurs when two quantum particles become linked such that the state of one instantaneously determines the state of the other, no matter the distance between them. In a quantum computer, entanglement enables qubits to coordinate in a way that classical bits cannot, allowing for computations that can be exponentially faster than traditional approaches. Once the basic concepts of quantum computing were established, the next critical challenge was to create algorithms that could exploit qubits' power. In 1994, physicist Peter Shor introduced a landmark algorithm capable of factoring large numbers far faster than any known classical algorithm. This was revolutionary, since number factoring is fundamental to RSA encryption, which underpins much of modern digital security. A quantum computer running Shor's algorithm could potentially crack encryption that protects online communications. Just 2 years later, in 1996, Love Grover developed another pivotal algorithm, one that could search unsorted databases more efficiently than classical methods. Whereas traditional computers check each entry one by one, Grover's algorithm enables a quantum search that is significantly faster. This demonstrated quantum computing's potential to enhance many types of tasks, from optimization to artificial intelligence. These theoretical breakthroughs galvanized both academic researchers and commercial players. The global pursuit of a practical quantum computer was now fully underway, but building such a machine has proven extremely difficult. Quantum states are inherently fragile and easily disrupted by factors like temperature, electromagnetic noise, and environmental interference. Creating a stable qubit is one of the greatest engineering challenges of our time. To address this, researchers have developed various experimental strategies. Trapped ions. This method involves isolating charged atoms using electromagnetic fields and controlling them with laser pulses. Each ion functions as a qubit, and their quantum states are manipulated through precisely timed laser interactions. This approach has shown considerable success in laboratory settings, leading to the development of small-scale quantum machines. Superconducting circuits. Using materials that conduct electricity without resistance at ultra-cold temperatures, scientists have built circuits that behave like artificial atoms. These are used as qubits in quantum processors. Companies such as IBM and Google have made significant headway here. Google's Sycamore processor made headlines in 2019 when it achieved quantum supremacy by solving a task in seconds that would have taken a classical supercomputer thousands of years. Topological qubits, a more speculative yet promising approach. Topological qubits aim to encode data within the global structure, or topology, of quantum states. Theoretically, this makes them more resistant to error, addressing one of quantum computing's major hurdles: reliable error correction. While we're still far from having large-scale, fully operational quantum computers, substantial progress has been achieved. In addition to better hardware, scientists are rapidly advancing quantum error correction, quantum communication, and quantum cryptography. The possibilities of quantum computing extend well beyond just faster processing. It holds the potential to solve challenges that are currently beyond even the most powerful classical systems. Fields like materials science, pharmaceutical development, and artificial intelligence stand to benefit greatly. For example, quantum simulations of molecular interactions, down to atomic detail, could lead to novel drug discoveries, better energy storage technologies, and the creation of materials we cannot yet imagine. Today, tech giants such as Microsoft, IBM, and Google are investing heavily in quantum research, while innovative startups like Rigetti Computing and IonQ are pushing the boundaries of what's possible. Governments worldwide are also funneling funding into national quantum initiatives, recognizing the immense potential across industries, from finance to healthcare. However, this revolution also presents new risks. If quantum computers can dismantle current encryption methods, how can we secure our data? This is where quantum cryptography comes into play, offering new security protocols based on the fundamental principles of quantum mechanics. In conclusion, quantum computing remains a young and rapidly evolving field. Yet its transformative power is already clear. From solving problems once deemed unsolvable to unveiling entirely new technological frontiers, quantum computing could represent the next major chapter in humanity's mastery of information, and perhaps even the universe itself. Unifying the cosmos, the pursuit of a grand universal theory. Imagine each puzzle piece symbolizing a different component of the cosmos, the fundamental forces, the properties of matter, and the very fabric of space and time. Now picture these pieces coming together seamlessly to form a single, all-encompassing image that explains the entire universe, from the tiniest particles to the grandest galaxies. This is the ultimate ambition of physics, a grand unified theory, often referred to as a theory of everything, TOE, a single conceptual framework capable of explaining all natural forces in one unified structure. For generations, scientists have chased this elusive objective. Although it continues to be one of science's most formidable challenges, considerable progress has been achieved. Let's explore the journey that has brought humanity closer to uncovering this profound and unifying theory. By the early 1900s, physics had already divided into two principal domains. The first was classical mechanics, which accurately described the motion of objects in everyday experience. The second was electromagnetism, the field that explains electric and magnetic interactions. This area had been elegantly unified in the 19th century by James Clerk Maxwell, whose equations demonstrated that light itself is an electromagnetic wave, a synthesis of electricity and magnetism into a single theory. But the landscape of physics shifted dramatically with the introduction of two revolutionary ideas: quantum mechanics and general relativity. These theories redefined our understanding of the universe from vastly different perspectives. Quantum mechanics, developed in the early 20th century by trailblazers like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, revealed that particles at the microscopic scale behave in non-intuitive ways. Rather than acting as solid entities, particles exhibit wave-like characteristics, and their behavior is governed by probabilities and uncertainties. Concepts like wave-particle duality and Heisenberg's uncertainty principle dismantled the deterministic worldview of classical physics. Meanwhile, Albert Einstein's 1915 theory of general relativity revolutionized the concept of gravity. Rather than being a force in the Newtonian sense, Einstein proposed that gravity results from the curvature of space-time caused by mass and energy. This new perspective replaced Newton's gravity and provided accurate predictions for phenomena involving extreme gravity, like black holes and the evolution of the cosmos. Although each theory, quantum mechanics and general relativity, proved highly effective in their respective arenas, they were fundamentally incompatible. Quantum mechanics governs atoms and subatomic particles, while general relativity applies to large-scale structures like stars and galaxies. Yet no unified theory could reconcile the two. The first significant leap toward unification came with the emergence of quantum field theory, QFT, in the mid-20th century. QFT integrated quantum mechanics with special relativity, laying the groundwork for describing how particles interact through force fields. A major breakthrough followed. Physicists discovered that three of the four fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force, could be described within a unified framework. This achievement culminated in what is now known as the Standard Model of particle physics. The Standard Model provides a detailed description of fundamental particles and the interactions among them. A milestone within this model was the successful merging of electromagnetic and weak nuclear forces into what became known as the electroweak theory in the 1970s. This effort earned Sheldon Glashow, Abdus Salam, and Steven Weinberg the Nobel Prize in Physics in 1979. In the 1980s, another triumph occurred: the prediction and later discovery of the Higgs boson, a particle that explains how other particles obtain mass, brought completeness to the Standard Model. However, a crucial piece remained missing: gravity. Gravity, still best described by Einstein's general relativity, remains absent from the quantum framework. No one has yet succeeded in integrating gravity with the other three forces using quantum principles. This gap is precisely where the dream of a theory of everything becomes essential. By the 1980s, attention turned toward an audacious idea: that all matter and forces might be manifestations of tiny, vibrating objects called strings. String theory proposes that the universe's most basic units are not point particles, but rather one-dimensional strings vibrating at different frequencies. Each vibrational mode corresponds to a different particle or force. What makes string theory compelling is that it offers a potential unification of quantum mechanics and general relativity. It provides a mathematical space in which gravity naturally arises from string vibrations, mediated by a hypothetical particle known as the graviton, which transmits gravitational force at the quantum level. String theory also introduces a radical concept: extra dimensions. Beyond the three spatial dimensions we experience, height, width, depth, string theory posits that there may be 10 or 11 total dimensions. These extra dimensions are believed to be compactified or curled up so tightly that they remain imperceptible to current instruments. Despite its elegance and potential, string theory remains speculative. It has not yet produced testable predictions. and its complex mathematical structure makes it difficult to verify experimentally. Some critics argue that string theory veers too far into abstraction, while its proponents believe it remains our best hope for unification. But string theory is not the only idea vying for the title of a theory of everything. An alternative approach known as loop quantum gravity, LQG, seeks to merge quantum mechanics with general relativity without relying on strings. LQG posits that spacetime itself is quantized, consisting of tiny, discrete loops. This approach preserves the core ideas of Einstein's theory while avoiding the need for extra dimensions or string-like entities. Though loop quantum gravity is still in an earlier stage of development compared to string theory, it offers a more direct bridge between quantum principles and general relativity and continues to be explored as a viable contender. So, how close are we to achieving a theory of everything? Despite incredible advancements over the last century, the final synthesis of all four forces, gravity, electromagnetism, and the strong and weak nuclear forces, has yet to be fully realized. One of the greatest obstacles lies in the vastly different scales involved. Quantum mechanics describes phenomena on the tiniest scales, while general relativity governs massive cosmic structures. To unify them, physicists must develop entirely new mathematical frameworks and conceptual tools, ones that may redefine how we think about the universe itself. The pursuit of a theory of everything is not just about solving equations, it's a journey driven by humanity's curiosity, creativity, and deep desire to understand our place in the cosmos. Whether string theory, loop quantum gravity, or another yet undiscovered idea ultimately provides the answer, this quest represents the very heart of theoretical physics. In the end, the theory of everything is more than a scientific theory. It is a philosophical pursuit, a way to comprehend the deepest truths of existence, and it will continue to inspire generations of scientists, dreamers, and thinkers for years to come. Hidden Realms, Exploring Extra Dimensions and Brain Theory. Imagine living in a world that's completely two-dimensional, like being stuck on a flat sheet of paper. In this realm, movement is only possible forwards, backwards, left, and right. Now, imagine someone tells you there are directions you can't perceive, paths that move above and below your flat plane. Although unimaginable at first, this is the core idea behind extra dimensions in modern physics, a concept that defies conventional notions of space and shakes our understanding of reality itself. The possibility that more dimensions exist beyond the known three, length, width, and height, has intrigued physicists for over 100 years. Yet it wasn't until the late 20th century, with the rise of string theory and the evolution of brain theory, that the notion of extra dimensions gained a concrete, mathematically robust foundation. Surprisingly, this concept isn't new. The earliest serious proposition to connect gravity and electromagnetism through an additional dimension dates back to the 1920s. Physicists Theodore Kaluza and Oscar Klein developed a theory suggesting that gravity could be represented by a fifth dimension, added to the four we already know, three of space and one of time. Klein expanded on Kaluza's idea, proposing that this extra dimension is compact, rolled up so tightly that we can't detect it. This model, known as the Kaluza-Klein theory, was a daring effort to unite nature's forces, though it remained purely theoretical at the time. As physics advanced, particularly with the establishment of quantum theory and Einstein's relativity, the idea of extra dimensions re-emerged, this time playing a vital role in shaping string theory. By the 1980s, string theory had become a leading framework for unifying the fundamental forces of the universe. Instead of viewing particles as tiny points, string theory describes them as infinitesimal, vibrating strings, where each unique vibration corresponds to a different particle or force. For this framework to be mathematically consistent, however, the theory requires more than the usual 4 dimensions, 3 of space and 1 of time. In fact, it demands a total of 10 dimensions, 9 spatial and 1 temporal. But if these extra dimensions exist, why don't we observe them? String theory answers this with the concept of compactification, the idea that these additional dimensions are tightly curled up at subatomic scales, hidden from our current ability to detect them. This concept was essential in making string theory a coherent and workable model. As string theory grew more sophisticated, attention turned to another idea: brains, short for membranes. Brains are multi-dimensional objects that can exist within these extra dimensions. While particles are considered zero-dimensional points, and strings are one-dimensional, brains can possess multiple dimensions. For example, a 2-brain is like a 2-dimensional surface, while a 3-brain has 3 dimensions, similar to a cube. One revolutionary idea that emerged from M-theory, a broader framework that encompasses various versions of string theory, was that our universe itself could be a 3-brain existing within a higher dimensional space. According to this view, everything we observe, from planets to galaxies, is confined to this 3-brain, while additional dimensions and possibly even other brains lie beyond our perceptual reach. An especially bold implication of brain theory is that gravity may not be limited to our 3-dimensional brain. Unlike the other forces, electromagnetism, the strong force, and the weak nuclear force, gravity might extend into the higher dimensions. This could explain why gravity appears so much weaker. It may be diluted as it spreads into realms beyond our perception. So, what do extra dimensions and brain theory suggest about the nature of the universe? These theories bring forward dramatic and revolutionary ideas about space, time, and the fundamental forces that govern reality. Here are 4 major implications. 1. Unifying nature's forces. Extra dimensions may be the key to merging all fundamental interactions. In string theory, the inclusion of extra dimensions provides a structure where particles and forces, including gravity, can be described within a single theoretical framework. This brings scientists closer to the long-standing vision of a theory of everything. 2. Hidden worlds. If dimensions beyond the visible 3 exist, this opens the door to the existence of realms beyond our perception. According to brain theory, our universe could be just one 3-dimensional brain floating within a higher dimensional expanse. Other brains might exist nearby, potentially forming parallel universes that remain invisible and inaccessible to us. 3. Dark matter and dark energy. Some researchers believe these theories could help explain mysteries such as dark matter and dark energy, which together make up most of the universe's content. Although we can't directly detect these phenomena, extra dimensions might allow for interactions with hidden forms of matter or energy, offering clues to their true nature. 4. The birth of the cosmos brain theory could also reshape our understanding of cosmic origins. One compelling hypothesis suggests that the Big Bang might have occurred due to a collision between brains. In this view, the creation of our universe could have been just one result of a much larger and more intricate cosmic process involving higher dimensional entities. Despite its beauty and potential, brain theory and the concept of extra dimensions remain speculative. To date, no direct evidence of higher dimensions or brains has been observed. While there is hope that future particle collider experiments or cosmological observations may uncover hints of their presence, we are still exploring the theoretical frontier. Yet as technology evolves and experimental tools improve, we may inch closer to verifying these radical ideas. Until then, extra dimensions and brain theory remain one of the most compelling avenues of exploration in theoretical physics, challenging our assumptions and expanding the boundaries of human thought. Ultimately, the idea of hidden dimensions offers a glimpse into a vast and complex universe, far beyond the limits of ordinary experience. These theories don't just change our understanding of physics, they invite us to reimagine reality itself, daring us to see the cosmos through a far more intricate and mysterious lens. Infinite realities, the concept of the multiverse. Imagine an endless archive that contains every conceivable book you could think of. In this boundless repository, each book symbolizes a distinct universe, with its own unique set of natural laws, timelines, and events. Some resemble our world with only minor differences, while others are drastically different, governed by entirely unfamiliar physics. This colossal library is an analogy for the multiverse, a sprawling, ever-growing collection of parallel universes that may exist alongside our own. The notion of the multiverse is one of the most profound and hotly debated ideas in current physics. It proposes that our universe is just one of many, potentially infinite, each representing a different version of reality. But where did this radical idea begin, and how has it developed over time? The earliest hints of a multiverse can be found in the early 1900s, during the birth of modern physics. The emergence of quantum mechanics and advances in cosmology introduced new frameworks for understanding the nature of reality. In quantum physics, particles do not move in strictly predictable ways. Instead, their behavior seems governed by probabilities. This led to the famous Copenhagen interpretation, which posits that particles may exist in multiple states simultaneously until measured or observed. However, the multiverse idea took a bold turn with the many worlds interpretation, MWI, of quantum mechanics, introduced by physicist Hugh Everett in 1957. Everett proposed a revolutionary idea. Rather than the universe selecting a single outcome when a quantum event occurs, every possible result happens, but in a different, separate universe. Think of flipping a coin. Instead of the outcome being either heads or tails, both results occur, each in its own parallel universe. In this view, each choice or possibility causes the universe to branch, creating an ever-growing tree of alternate realities. This interpretation fundamentally shifted how physicists thought about quantum behavior. According to it, our universe is just one branch among countless others, each representing different outcomes of quantum events. Initially, this concept was considered more of a mathematical curiosity than a serious physical theory. But it provided a compelling theoretical foundation for the idea of the multiverse. While Everett's theory laid the groundwork, it was the work of cosmologists in the latter part of the 20th century that moved the multiverse into the realm of mainstream science. The development of the inflationary model of the universe by Alan Guth in the early 1980s gave the multiverse concept a major boost. Cosmic inflation is the idea that just moments after the Big Bang, the universe experienced a period of rapid, exponential expansion. During this time, tiny quantum fluctuations were stretched across vast distances, seeding the large-scale structures, like galaxies, that we see today. But inflation theory had a stranger implication. If inflation occurred in some regions of space differently than others, then it could result in isolated pockets of space expanding into entirely separate universes. This led to the idea of eternal inflation, where inflation never completely stops, continuing indefinitely in some regions and constantly spawning new bubble universes, each with its own unique laws of physics. This scenario, known as the bubble universe model, reframes the Big Bang as just one of many such events, each bubble representing a different universe with different physical properties, such as the gravitational constant, the speed of light, or even the fundamental forces themselves. As this idea gained popularity among cosmologists, it found strong resonance within string theory, a mathematical framework aimed at unifying all known forces. In string theory, the fundamental components of reality aren't particles, but vibrating one-dimensional strings, which require additional spatial dimensions beyond the familiar three of space and one of time. String theory predicts a vast number of possible solutions to its equations, each corresponding to a universe with its own physical rules. This concept is known as the string landscape. In this picture, the multiverse becomes an unavoidable consequence of the many ways that these extra dimensions can be shaped or compactified. Each possible configuration of these dimensions results in a different set of physical constants, effectively creating a separate universe. The landscape is so vast that some physicists believe it is virtually certain that other universes exist. According to this view, the apparent fine-tuning of our universe's laws may simply be due to the fact that in an infinite set of universes, some will naturally support life just by chance. If the multiverse hypothesis is accurate, it forces us to reconsider the foundations of existence. Here are some of the most significant implications. 1. Explaining fine-tuning. One of the deepest puzzles in physics is why certain constants, like the strength of gravity or the mass of elementary particles, are precisely balanced to allow the existence of life. The multiverse theory offers a solution. With infinite variations, some universes will randomly have the right conditions, and we happen to be in one of them. 2. Redefining probability. If every possible outcome of every quantum decision occurs in some universe, our traditional view of probability and chance is thrown into question. The idea that everything that can happen does happen somewhere challenges how we understand fate and choice. 3. Observational challenges. One of the biggest issues with the multiverse theory is that in most versions, these other universes are permanently inaccessible. They don't interact with our own, making them impossible to observe directly. This raises a philosophical question. Is a theory truly scientific if it cannot be tested? Despite the groundbreaking implications, the multiverse remains a highly speculative theory. No direct evidence has yet been found to support the existence of other universes, and verifying their presence presents a monumental challenge. Still, the concept continues to inspire cutting-edge research in physics, from cosmology and quantum theory to string theory. Should we ever gain the ability to test the multiverse through advanced cosmological observations or new particle physics discoveries, we may open an entirely new chapter in our understanding of the cosmos. In such a reality, our universe would no longer be unique, but just one in a sea of infinite possibilities. Even if the multiverse remains unproven, the idea encourages us to ask profound questions about what reality truly is, why the universe exists as it does, and what may lie beyond our cosmic horizon. For now, it remains a compelling, mind-expanding theory, one that challenges the boundaries of imagination and hints at the limitless scope of the cosmos. The black hole information mystery. Picture yourself facing a colossal black hole, among the most enigmatic and powerful phenomena in the cosmos. As you draw nearer, something strange becomes apparent. Objects, light, and even information that fall into it appear to vanish, completely and irretrievably. But does information truly get destroyed? Or does it endure in ways that remain beyond our current comprehension? This is the core dilemma known as the black hole information mystery, one of the most perplexing issues in present-day theoretical physics. To delve into this riddle, we must look back at its origin, tracing the pivotal discoveries that led to it, and examining the persistent scientific efforts to solve it. This paradox took shape thanks to the legendary physicist Stephen Hawking in the 1970s. Before his groundbreaking work, black holes were generally viewed as gravitational sinks, so powerful that even light couldn't escape. The boundary beyond which escape becomes impossible is called the event horizon. Once crossed, not even information was believed to return. But Hawking's research upended this classic idea. In 1974, he introduced a radical concept. Black holes emit radiation. This phenomenon, later dubbed Hawking radiation, stems from quantum effects near the event horizon. It's as though black holes gradually leak energy, and over time, this could cause them to shrink and ultimately disappear. This finding was revolutionary. It suggested black holes weren't eternal, they could dissipate. But this insight also gave rise to a troubling paradox. According to quantum physics, information about the state of a system, whether that's particle positions, energy properties, or quantum states, can never be completely destroyed. Even if a black hole vanishes through radiation, the information it contains should theoretically remain intact. After all, information conservation is a fundamental pillar of quantum theory. And here lies the contradiction. If a black hole evaporates and all that remains is Hawking radiation, which appears to be random and unstructured, then where did the original information go? The radiation doesn't seem to encode any details about what was consumed by the black hole. This suggests that the information is gone forever, directly violating quantum mechanics' most basic rule. Imagine you toss a detailed book into a black hole. You'd expect that even if the book becomes inaccessible, the data it carried still exists in some preserved state. But Hawking's theory implied that when the black hole fully evaporates, it's as if the book and its contents never existed. The information would be completely erased. This deeply unsettled physicists. If black holes truly obliterate information, then quantum mechanics, long considered a bedrock of physics, might be incomplete, or worse, fundamentally flawed. This tension gave birth to the information paradox, the mystery of whether data that enters a black hole is gone forever or remains intact in a form we do not yet understand. The paradox has since ignited decades of intense debate among physicists. Some believe that information is truly destroyed, which would require a significant revision of quantum theory. But many others, including thinkers like Leonard Susskind and Juan Maldacena, strongly defend the idea that information must be preserved. These defenders have introduced several ideas aiming to reconcile the paradox. One of the most prominent is the holographic principle. This theory proposes that information swallowed by a black hole isn't lost, but rather encoded on the event horizon itself in a two-dimensional format. The analogy is similar to a hologram, where a flat surface holds the data needed to generate a three-dimensional image. According to this view, the surface area of the black hole, its event horizon, retains all the information about what fell in. Although the data might not be directly observable, it might subtly influence the radiation the black hole emits, allowing information to be preserved in some hidden or scrambled form. Another bold solution involves the firewall hypothesis. This controversial idea, developed by physicists such as Alessandro Strominger and Samir Mathur, proposes that the event horizon isn't smooth and passive as once believed. Instead, it could be a zone of intense, violent energy, a firewall capable of obliterating anything that crosses it. If this were true, it could potentially solve the paradox by suggesting a mechanism through which information might be processed or even preserved in an entirely new way. But this idea is also highly contentious, as it would require a radical overhaul of our understanding of space-time and general relativity. For now, the information paradox remains unresolved. While the discovery of Hawking radiation profoundly changed how scientists think about black holes, it also introduced one of the most vexing puzzles in modern science. Researchers continue to explore this paradox from multiple angles, and new theoretical ideas are constantly surfacing. Some scientists believe that unlocking the paradox may depend on finding a unified theory of quantum gravity, one that blends quantum mechanics and general relativity into a single, consistent framework. This grand theory still eludes us. Meanwhile, new experiments and observations are underway. Scientists are examining gravitational waves in developing more advanced telescopes and detectors to study black holes and their event horizons in greater detail. These efforts might eventually yield the evidence needed to understand whether information can somehow escape a black hole or if it truly disappears forever. At its heart, the information paradox challenges our assumptions about reality. Does the universe obey the absolute rules of quantum mechanics, or do black holes represent an exception, a region where the laws of physics as we know them no longer apply? Whether information is irretrievably lost or subtly retained, this paradox opens a window into the deepest mysteries of existence. It pushes us closer to understanding the true nature of space, time, and the universe itself. For now, the riddle endures, a compelling mystery that underscores the staggering complexity and wonder of the cosmos we are still striving to comprehend. Breakthroughs in the pursuit of fusion. Energy. Nuclear fusion, the same force that fuels the stars, including our very own sun, is the most power-efficient process known to modern science. It generates immense energy by merging lightweight atomic nuclei, such as hydrogen, into heavier elements like helium. For decades, scientists have been attempting to reproduce this stellar reaction here on Earth, hoping to unlock a nearly infinite, environmentally friendly source of power. But how far have we progressed in this ambitious scientific journey? To appreciate the revolutionary strides made in fusion energy research, it's essential to retrace the development of the field and highlight the scientific innovations that have guided its evolution. The narrative of nuclear fusion research dates back to the 1930s, when physicists such as Hans Bethe first unraveled how stars generate their energy. Bethe's pioneering work showed that stars, including the Sun, sustain themselves by fusing hydrogen atoms into helium via a sequence of nuclear reactions. This process, now called the proton-proton chain reaction, unleashes vast amounts of energy in the form of light and heat, maintaining the star's brilliance and high temperatures. Bethe's contributions were foundational, setting the stage for future attempts to create fusion energy artificially. But it wasn't until the 1950s that humanity seriously began developing fusion as a feasible power source. During this time, the idea of nuclear fusion reactors, devices that could fuse atomic nuclei and harness the energy produced, started to materialize. Early progress came through a technique called magnetic confinement fusion, which employs intense magnetic fields to trap hot plasma, a superheated, electrically charged gas, in a stable, enclosed environment long enough to initiate fusion. This method inspired the creation of the tokamak, a toroidal or donut-shaped reactor built to confine plasma at extremely high temperatures, often reaching millions of degrees Celsius without allowing it to come into contact with the reactor walls. In the early 1960s, Soviet scientists, including Andrei Sakharov and Lev Artsimovich, achieved notable advancements by designing the first tokamak reactors, which were able to attain the intense heat levels necessary for fusion to occur. However, despite their promise, these early machines couldn't maintain the necessary stability or produce more energy than they consumed. On Earth, achieving practical fusion remained out of reach. One of the biggest obstacles was the challenge of heating plasma to temperatures far hotter than any known material could withstand, around 100 million degrees Celsius, and keeping it confined long enough for sustained fusion reactions to occur. No materials could survive direct contact with such conditions. Yet, the dream of harnessing fusion energy persisted. In recent decades, there has been tremendous progress, driven by emerging technologies and growing global collaboration. One of the most ambitious and transformative initiatives is the creation of the International Thermonuclear Experimental Reactor, ITER, an unprecedented effort to construct the world's largest and most sophisticated fusion reactor. Located in southern France, ITER is a cooperative project involving 35 nations, including major contributors like the European Union, the United States, Russia, and China. ITER's goal is to prove that nuclear fusion can be a viable and sustainable energy source by achieving net positive output, that is, producing more energy from fusion than is required to sustain the plasma. Based on the tokamak design, ITER integrates advanced technologies to operate under extreme conditions, temperatures and pressures once considered unreachable. In 2021, ITER reached a significant milestone with the successful installation of its superconducting magnets. These magnets, cooled to near absolute zero, are critical for generating the magnetic fields necessary to confine the plasma. Unlike traditional magnets, superconducting ones produce much stronger fields, allowing ITER to reach the required fusion conditions. Although ITER is still being constructed and isn't expected to be fully operational until the late 2020s, nuclear fusion research continues to make notable progress elsewhere. In the same year, 2021, the National Ignition Facility, NIF, in the United States achieved a breakthrough. Unlike ITER's magnetic method, NIF utilizes laser-driven fusion, specifically inertial confinement fusion. This process involves directing powerful laser beams at a small hydrogen fuel pellet, compressing it to the extreme temperatures and pressures found at the center of stars. That year, NIF announced it had achieved a record-breaking energy output, generating nearly 1.9 megajoules from a single fusion reaction, a major step toward reaching ignition, the point where fusion generates more energy than is required to start the reaction. This achievement was significant because it demonstrated that controlled fusion is feasible in laboratory conditions, pushing the frontier of what's technologically achievable. However, major hurdles still remain before fusion can be scaled into a reliable power source. The next objective for NIF and similar facilities is to expand the process, improve energy efficiency, and sustain reactions for longer periods, ensuring they yield more energy than they consume. Looking ahead, these advances point to a thrilling future, the potential of clean, essentially limitless power. Unlike nuclear fission, which fuels current nuclear reactors, but produces dangerous long-lasting waste, fusion produces minimal radioactive byproducts. Its fuel, mainly isotopes of hydrogen like deuterium and tritium, is abundant, with deuterium easily extracted from seawater, making it an incredibly sustainable resource. Nonetheless, substantial challenges remain. The technical complexity of achieving sustained, net-positive fusion on Earth is immense. Reactors must endure extreme conditions, maintain stable plasma, and incorporate materials that can survive without degrading under constant heat and pressure. Moreover, the financial cost of building and operating these reactors remains very high. Even so, the accelerating pace of innovation in the field is encouraging, as governments and private sectors continue to invest heavily in fusion research. The long-standing vision of harnessing stellar energy on Earth grows increasingly achievable. Physicists, engineers, and researchers worldwide are laying the foundation for a new era, a cleaner, more sustainable planet powered by the same process that ignites the stars in our night sky. Though the finish line hasn't yet been crossed, the pursuit of practical nuclear fusion continues, each advance bringing us closer to unleashing the most powerful energy source known to science, a source that could forever redefine how we energize our world.